In late 2024, BOE Technology placed a glass core substrate on a conference table in Chengdu. The company is known primarily for display panels. The object it was presenting is not a display component. It measures roughly 115 by 115 millimeters, carries approximately 3,000 connections across 20 laminated layers, and sits in the interposer class, the category of components whose sole function is to route signals between the silicon dies above and the printed circuit board below. The surface is unremarkable, matte, slightly cool to the touch, heavier than its footprint suggests. Nothing on the exterior announces what the interior is doing. We are going to take this object apart from that exterior inward, layer by layer, and the deepest layer is going to expose something the headline framing, glass substrate replaces copper interconnect, does not actually say and cannot honestly claim. The cuts run from the outer package surface into the first 9-layer buildup region to the boundary where buildup meets glass core, into the glass core itself, and the dimensional physics it solves, through the through-glass vias where copper persists unchanged, down to the electrical transmission limits that define where glass improvement ends and a different problem begins, and finally to 3 things this dissection cannot settle from the physical record alone. The substrate arrives as a finished laminate. It is not a die. It is not a wafer. It is the package component whose job begins where the chip ends and ends where the board begins. BOE's published dimensions place this object in the 115mm class, and that measurement is not incidental. It is the first structural fact the surface communicates, because 115mm is approximately the panel size at which organic core substrates, the bismuth imide triazine laminates that have served the industry for decades, begin to show systematic warpage under the thermal loads of assembly and operation. The package is this size because the compute density it must support demands it. Multiple silicon dies, potentially including high bandwidth memory stacks mounted alongside large logic dies, require a package footprint that no smaller format can accommodate without compromising the connection density. The size is not a design preference. The size is the load the package must carry, and the load is what makes the core material a question worth reopening. At smaller package sizes, organic laminates hold flat well enough. The sub-10 micron alignment tolerances that fine pitch interconnects require are achievable when the panel dimensions are small enough that thermal expansion across the full diagonal stays within a manageable range. As the panel grows, the accumulated displacement from thermal cycling exceeds that range. The organic core begins to flex. The fine pitch connections lose registration. The package fails before it reaches the board. The object on the table is 115mm because the system it serves requires that footprint, and the footprint requires a different core. Removing the surface finish exposes the first of 2 9-layer buildup regions. Each buildup layer is a dielectric film with patterned copper traces embedded in it, connected vertically to the layers above and below through laser-drilled vias. The traces in the upper buildup layers, closest to the die, are the finest in the package. BOE's published specifications cite 2-micron line and space targets for the upper buildup levels, which places this object at the frontier of what advanced packaging lithography can currently produce at scale, though independent metrology confirmation of those dimensions in production material is not publicly available. The 9-layer count on each face of the glass core is not a record in isolation. Some advanced organic substrates reach comparable buildup counts. What distinguishes 9 layers on glass from 9 layers on an organic core at this panel size is the flatness of the platform on which those layers are built. The count is a proxy for a solved registration problem, not a standalone achievement. The reason 9 layers are required at all is geometric. Die side pitch, the spacing between the copper pillars or solder bumps on the underside of the chip, ranges from roughly 40 to 100 microns on current advanced packages. Board side pitch is measured in hundreds of microns, often above 200. 9 buildup layers is what the fan-out mathematics requires to transition thousands of connections from silicon side density down to board side density without trace crossings and without violating minimum spacing rules at any intermediate level. Each layer is one redistribution step. Fewer layers would require sharper angular routing, which at fine pitch produces electrical coupling between adjacent traces. More layers would add cost and process complexity without improving the geometry. 9 is not an arbitrary number. It is the solution to a simultaneous routing and spacing constraint across a connection count in the thousands. At the boundary between the buildup stack and the glass core, the via geometry changes in a way that marks a functional transition. The buildup vias are layer to layer, small diameter, laser-formed, connecting adjacent dielectric films. The through-glass vias that penetrate the core are formed through a structurally different material, thicker, more brittle, requiring different hole formation chemistry, and they span the full thickness of the core rather than a single thin film. Glass core thickness in this class of package sits in a range from roughly 100 to 300 microns based on published industry comparisons of comparable glass core packages. BOE has not publicly confirmed the specific core thickness for the 929 configuration. The glass core itself carries only 2 routing layers. For a component that the outline nominates as the structural center of a 20-layer stack, 2 internal routing layers is a stark number. It is not a limitation. It is a deliberate division of labor. The 2-layer glass core is not designed to carry routing traffic. The 9-layer buildup stacks on each face handle the routing work. The glass core's function is to provide the dimensional spine that keeps both buildup stacks in registration with each other and with the die side and board side connection fields across the full panel area under temperature change. A spine needs to be rigid and stable. It does not need to be a signal highway. The question of how many routing layers a structural element needs is answered empirically by what the buildup layers above and below can handle. Less than the headline layer count suggests, precisely because the structural work is separated from the routing work. The architecture encodes that separation visibly in the layer counts. 9, 2, 9. The physical property that makes glass the material for that structural role is the coefficient of thermal expansion. Organic core laminates expand and contract at rates between roughly 14 and 17 parts per million per degree Celsius. Silicon, which is what the dies mounted on this substrate are made of, has a coefficient of thermal expansion near 3 parts per million per degree Celsius. Glass compositions used for core substrates, including those produced by Corning and AGC, the 2 largest external suppliers. BOE sources glass internally, and its specific composition and coefficient of thermal expansion are not publicly confirmed, have coefficients of thermal expansion in the range of 3 to 4 parts per million per degree Celsius, closely matching silicon. The organic laminate's coefficient of thermal expansion does not match silicon. It never has. For decades, the industry compensated through design rules, keep-out zones around sensitive via fields, substrate thickness adjustments, mechanical reinforcement structures. Those compensations work at small panel sizes, at 115 millimeters across the thermal excursion from room temperature to the roughly 260 degrees Celsius peak of a solder reflow process. The accumulated lateral displacement of an organic core at 14 parts per million per degree Celsius reaches magnitudes that exceed the alignment budget for 2-micron vias. Across a 115 millimeter panel over a 200 degree temperature window, lateral displacement in an organic core accumulates to more than 300 micrometers total, distributed across a substrate where the vias that must remain aligned are spaced 2 to 10 micrometers apart. Glass, matching silicon's thermal behavior, moves with the dies rather than against them. The registration holds. This is the structural problem the glass core solves, and it is the problem that no incremental improvement to organic laminate chemistry has resolved at large panel sizes. The mismatch between organic core materials and silicon is a materials physics constraint, not a process maturity constraint. The glass core does not improve on organic laminates in the way that a newer laminate formulation improves on an older one. It steps outside the coefficient of thermal expansion range that organic materials occupy and lands in the range that silicon occupies. The flatness the buildup layers require to maintain fine pitch registration is a consequence of that step, not a separate achievement. Opening the glass core to examine the through-glass vias is where the headline description of this substrate becomes actively misleading and where the dissection finds its sharpest result. The vias are copper-filled. Every vertical signal path in this package, through each buildup layer, through the glass core, at every junction between routing levels, is electroplated copper. BOE's own published cross-sections presented at industry conferences are consistent with teardown analyses of comparable glass core substrates from other manufacturers, all of which show conventional copper fill in the through glass via holes. The substrate does not replace copper with an alternative conductor. It replaces the organic dielectric as the structural host for copper interconnect. Glass is the environment. Copper is still the conductor. Copper remains in place because no commercially available alternative conductor matches its combination of electrical conductivity, electroplating processability, and tolerance for the temperatures involved in package assembly. The through-glass via process, forming the hole by laser or mechanical means, depositing a seed layer to initiate copper adhesion, then electroplating to fill the via volume, is adapted from through-silicon via technology developed for three-dimensional memory stacking. The adaptation is not trivial. Glass fractures differently from silicon under the mechanical and thermal stresses of drilling, and the surface chemistry for copper seed adhesion on glass requires treatment processes different from those used on silicon. The engineering to make copper adhere reliably inside a glass via is real work. But the conductor that results from that work is the same element that filled package vias in 2004. This layer of the dissection closes the question the headline opens: copper does not leave. The question is what copper's presence means for the electrical performance the substrate can deliver. The deepest layer of this substrate is not a physical stratum. It is the electrical physics that copper transmission lines obey at the signal frequencies that high-bandwidth memory interfaces and die-to-die interconnects operate on. At signal frequencies from roughly 50 to 100 GHz, the range where current and next-generation high-bandwidth memory interfaces and chiplet interconnect standards are operating or approaching, copper traces carry signals with acceptable loss over distances measured in a few millimeters. As trace length grows beyond 10 to 20 millimeters, attenuation in copper at these frequencies rises steeply. The precise crossover distance depends on trace geometry, dielectric loss tangent, and temperature. The underlying transmission line physics is well established and not contested. Glass as a dielectric has a lower loss tangent than organic laminate materials. Published materials characterizations place glass loss tangent in the low 10,000ths range and organic laminate loss tangent in the mid 10,000ths range. Lower loss tangent means less signal energy absorbed by the dielectric per unit length, which extends the distance over which a copper trace can carry a high-frequency signal within an acceptable signal-to-noise budget. The glass dielectric environment is better for copper than organic laminate. It is not transformative. The improvement glass provides to the copper link budget is real and measurable. It is also incremental relative to the challenge of connecting dozens of chiplets across a package that may reach 200 millimeters on a side, the scale that advanced artificial intelligence accelerator packages are approaching. At that scale, connecting logic dies to high bandwidth memory stacks and to each other across distances of 30, 50, or 100 millimeters with copper traces at 50 plus gigahertz produces attenuation and power consumption that the system cannot absorb. The glass substrate, by providing a stable, low-loss platform for fine copper traces, pushes that boundary outward. It does not eliminate it. The boundary remains. The next step past that boundary, for the longest, highest bandwidth links inside the package, is photonic interconnect. Optical waveguides or optical chiplets mounted within the package that carry signals as light rather than as current. Glass, as it happens, is a natural host material for optical waveguides. The substrate that was built to solve the organic laminate flatness problem is also the substrate that can, in principle, host the optical components that copper's physics eventually requires. The buried observation is that the glass core substrate is not the endpoint of the transition it represents. It is the platform that makes the next transition architecturally legible. The restriction that brought BOE into glass substrates also shapes what the architecture looks like from the inside. Organic laminate limitations at large panel sizes created the material problem. Limited access to leading-edge advanced packaging from external foundries under export restricted conditions created the supply chain incentive to develop internal capability. The substrate that results from those two pressures is optimized for a copper interconnect world that is already approaching its electrical boundary. The glass core is an answer to one constraint, the flatness problem, that simultaneously exposes the next constraint, the copper attenuation problem, with new clarity. The 20 layers do not describe a solved problem. They describe the precise geometry of where one solution ends and the following problem becomes visible. Three things this dissection cannot settle from the physical record alone. First, the gap between company claim and independent confirmation. BOE's qualification data for the 929 configuration is company reported. Thermal cycling results and bend testing figures presented at industry events describe performance within BOE's own qualification framework. No publicly available independent report covering the full board-level reliability protocol that JEDEC standards require for production packaging, including thermal cycling, drop testing, and humidity exposure at production sample volumes, has been published for this specific configuration as of mid-2025. The teardown analysis is consistent with sound construction. It does not confirm the reliability envelope across the full range of field conditions that production deployment requires. Those are different statements, and this dissection will not treat them as equivalent. Second, the node gap sits above the substrate. Glass core substrates improve the packaging layer. The dies that mount on them still require advanced lithography to produce. The most capable high-bandwidth memory dies and leading-edge logic chips are manufactured at process nodes that neither BOE's substrate business nor the most advanced domestically accessible silicon foundry capacity currently reaches. A world-class package hosting chips produced at constrained node access produces a system whose performance ceiling is set by the silicon, not by the quality of the package around it. Third, thermal management under high-power operation is an open physical question. Glass has lower thermal conductivity than organic laminates, which already conduct heat poorly relative to silicon or metal. As more power-hungry chiplets are assembled in a glass core package, the thermal resistance between the die junction and the board increases. Published thermal modeling for this substrate configuration under sustained high-power workloads is not available in the public record. Whether glass core packages can manage the heat flux that the artificial intelligence accelerator market they are being positioned for actually generates is a question the current qualification data does not answer. The dissection reaches the interior of this substrate with confidence. The construction is documented, the physics is established, and the constraint is legible in the geometry. What it cannot reach from the outside is the system-level performance under production workloads, the long-term reliability distribution across a production population, or the thermal behavior under the sustained power levels of deployed accelerator systems. Those require data that does not yet exist in the public record. Taken together, the 20 layers of BOE's 929 glass core substrate tell a consistent and internally complete story. The glass core is present because organic laminates flex at this panel size and fine connections require a stable platform. The 9-layer buildup stacks on each face are present because the geometric gap between silicon side pitch and board side pitch requires that many redistribution steps at this connection density. The copper fill is present in every via because no commercial alternative conductor exists for these currents and assembly temperatures. The lower loss tangent that glass provides over organic dielectric is present and measurable, and it extends the electrical operating range of copper traces in this package up to the frequency and distance boundary where the extension stops being sufficient. The layers do not describe a technology that has escaped its constraints. They describe a technology whose constraints have been precisely internalized and whose architecture is the legible record of that internalization at every depth. BOE's entry into glass substrates is the story of a materials processing capability built through years of large panel glass handling for display manufacturing, being redirected toward a packaging problem that the semiconductor packaging industry has been approaching from the silicon side for more than a decade. The object that results from that redirection is not a surprise from outside the industry. It is a convergence. Two different industries approaching the same physical limit from different material starting points, arriving at an object whose layered architecture encodes every pressure that produced it. The deepest layer of any substrate is always the same, the shape of the problem it was built to hold. That is what the 929 looks like from the inside out. The question is what to put on the table next. If you have a nominee for the next object to open up, put it in the comments, and we will decide what deserves the next cut. Subscribe if you want to be here when we make it.